Okay, is my screen visible to all of you?
Yes.
Okay, so welcome to 6th lecture of Advanced Electric Drives. And so far we have seen how the buck converter has evolved, and also some discussion on boost converter we have done. So basically what we saw in the last lecture, that boost converter is nothing but power flow from a current source to a voltage source, and that is how it can be visualized. So we all know that the structure for boost converter is this, and then this clearly shows that we are trying to form a current source over here, and we have a voltage stiff element over here on the load side. So basically we are having kind of power transfer from the current source to the voltage source. And then when we have this kind of arrangement, it is basically we are averaging the current. That means we are reducing the current by some average value. So when we turn on the switch, the current transfer to the load side is 0, and we turn off, let's say connect PT2, then it is basically the same current flowing to the load. So then we have this kind of relationship between the output current and the input current, and so we can say that this is basically a current buck converter. And because the power is balanced, whatever power is going as input must come out as output. So we have the boost operation for the voltage, and that we know. That's usually our understanding. So this expression what I have derived over here can also be realized when we go by balancing the volt second across the inductor. So question was there, I think from Ajay, that how to ensure the volt second balance. So again, see, what is volt second? Basically what we are trying to do is that the amount of positive voltage multiplied by the time that is applied across the inductor should be same as the negative voltage multiplied by time which is applied to the inductor. So we must ensure that this average value, let's say you take VL dt 0 to Ts, must be 0. Now what are the ways to realize this? How can we achieve this thing? That we will see little later. But this is the essence of this. Whatever we are applying on this side, this must be equal to. So these two areas must be equal. So there are many ways. See, one thing what we can do, we have, let's say, okay, I'm jumping little bit. Let's say some active switch is there. You can control the turn on and turn off of this switch, right? So using that, you can have the balanced amount of flux injected into the inductor. But before I realize these switches, I actually don't feel like discussing this part, so I will come back to this again. Fine. Today we will complete this realization. Now, based on the turn on and turn off time periods and the different forms of circuit, we have the output current and then the capacitor current and then the capacitor voltage derived over here. So we can draw all the waveforms now on basis of our understanding how the current is flowing and what it should look like. So up to this point, I hope that you are clear. There is no confusion, right? Clear?
Yes, sir.
So whatever we have seen so far is basically what we call as single stage power conversion, where we have power transfer from either from the voltage source to current source or from current source to voltage source. Now, in either of the case, we have only two possibilities. Either the output voltage can be less than the input voltage or it can be more than the input voltage. There is no third possibility. What at the most we can do is that we can club these two things in the same converter. So that we call as double stage. So we may have, let's say, first the buck operation and then the boost operation. So which means what? We will have power transfer from voltage source to current source and then from current source to voltage source. That's the meaning of buck and then boost. So that's why this converter is famously known as buck boost converter. So we may also have configuration like boost and then buck and then boost. So that depends on how you are arranging the power sources in the circuit. Am I clear?
Yes, sir. Yes, sir.
So this is one example how people have realized the buck boost converter. So this current stiff element, basically this behaves like a current source. Correct? So what is happening now when we connect this pole to throw 1, the power is transferred from this voltage source to this inductor. And then when we connect this pole to T2, then power is transferred from. So because the current direction cannot be changed suddenly in the inductor, so this will be maintained. The direction will be maintained. And hence, when you connect it here, the current flows like this. So we see the inversion in voltage at the output end also. So there may be configurations where we can avoid the voltage inversion. The polarity of the voltage can be same as the input voltage. These arrangements can be made. But this is just one example where we have power transfer first from voltage source to current source and then from current source to another voltage stiff element. So that is what we are seeing over here. And in a very similar way, we can have the waveforms for the inductor current and voltage, capacitor current and voltage. All these things can be derived. So the important part now to discuss over here is that how to realize these converters. When we are having the most common element in all the converters is this SPDT switch, and this is basically arranged in different manner to realize any converter. Let's say when we had buck converter, the pole is connected to the inductor and this is connected to the load end. And when we have boost converter, the source is basically connecting the inductor and then pole is connected to that. So different configurations we are having for different converters. But how to realize this? So obviously we cannot have any mechanical switch, that we are very much sure. So it could be one of the power electronic devices. So this is what we are going to discuss today. Which power electronic device you can have in the place of PT1 and PT2. Now, before going to that, we had seen some characteristics of ideal switch, which means what is basically the ideal characteristic that should be expected from the switch. Whether the actual switch fulfills partially this characteristic or doesn't fulfill partially, that we will see later. But first, what we should have as expectation from the switch that we have seen over here. So when we say that we have a switch, so definitely we may have two states for the switch. One where the circuit is open and another where the circuit is closed. Now this is called the off state and the on state. Now what we have during the off state, that there cannot be any current flowing from, through the switch, and whatever voltage you apply across the switch, it will be able to block. And then in the on state, we have any amount of current flowing through the switch, but the voltage drop across the switch is 0. And when I say the voltage blocking and current flowing capability, I am saying that it is bidirectional, which means any polarity of voltage can be blocked and any direction of current can be passed through this switch. This is the ideal switch. Now, going from one state to another state, the transition time is also 0 for the ideal switch. And the energy taken in that change in state is also 0. So this is the characteristic. So ultimately what we have, that during the conduction also the power is 0. During the transition also during the switching also the power is 0. And then there is no transition time. Now what we have to realize is basically something which is closer to this ideal characteristic. So this is IV characteristic of the ideal switch, and we have all the 4 quadrants being operated with that. So we may have positive current, positive voltage, positive current, negative voltage, negative current, negative voltage, and positive voltage, negative current. So all 4 conditions it can fulfill. Now let us come to real switch. What we have basically. So we have basically diode, BJT, MOSFET, IGBT, and so on. Many more switches could be there. So first switch, diode, we have seen that what are the characteristics. So we know that when the diode is forward biased, it can conduct any amount of current ideally. And when it is reverse biased, it can block any amount of voltage ideally. So what we are basically having here, the ideal characteristic where we have positive current and the negative voltage. But practically when we see the diode, there must be some forward biased voltage applied, at least say 0.7 volts applied across the diode for making it in conduction mode. And then it can continue with that amount of current. Let's say I'm drawing this in black characteristic. So that's why there is slight shift from the origin. This amount of voltage, what is coming on the voltage axis, this is, you can call the forward bias voltage or the saturation voltage. And then the characteristic goes, the current rises steeply in that. Then on the negative voltage side, again, we can continue with very big amount of blocking voltage up to a certain value, which is called the breakdown voltage. So until this breakdown voltage is reached, the diode can block this reverse voltage, reverse polarity voltage. But whenever you try to exceed this breakdown voltage, there will be sudden shoot through of the current through the diode. So this is like many a times damaging for the diode unless it is prepared or made for that application. Now in the characteristic here we see that this positive or the first quadrant characteristic, this is not exactly straight line. It is slightly shifted and then it is going slightly slant. So what we can understand from this characteristic is that it is basically equivalent to having some voltage against the direction of current flow and some resistance involved over there. So we can say some on-state resistance and some forward bias voltage or on-state voltage is there as equivalent circuit for the diode when it is conducting. So which means because these values are not very small or not very close to zero, so definitely we have some finite amount of power loss which is coming as I square R on and VR into I, where I is the current flowing through this diode. So this is what is the conduction loss, what we see in diode when we apply it to any circuit and it is forward biased. For the blocking state or for the off state, generally it behaves like a very good open circuit. That means the leakage current flowing through this device will be very small, something of the order of microampere or so, and hence the power loss can be regarded as zero. It's very small. So these are some of the discussions about diode. Then we have move on to a more controlled switch. So of course here in diode we have only two terminals, anode cathode. So these are only power terminals. There is no third control terminal. So this is uncontrolled switch. Now from here we are moving on to controlled switches. So first switch what we can have.
Sir,
yes, Sampath.
Sir, can you repeat the second quadrant point?
Which second quadrant point?
Sir, in diode, as you mentioned in the last class.
Yeah. So what did you not understand in this?
Sir, so characteristics are in first and third quadrant. So role of second quadrant.
So where is the characteristic in third quadrant? This is second quadrant, right? Positive current and negative voltage.
Okay.
Where is the third quadrant? This is current flowing and it has broken down. So that's not characteristic really. This is something not desired from the diode.
Yes, sir.
Okay, so now coming to BJT, which is basically a three-terminal device. We have collector, emitter, and base. So through base, the current which is injected into this base terminal, let's say the base current, is used for controlling this device. Now, based on how much current you are injecting in the base, that decides where the device is going to operate. So if I draw the characteristic for BJT, so ideally what happens that BJT can block any voltage in this direction. So here we are talking about NPN transistor. So it can block the voltage in this polarity and it can conduct the current in this direction. So the data sheet or the manufacturer do not guarantee anything about the reverse polarities of blocking voltage or current. So that is why this is what is recommended operation for the BJT. So the ideal characteristic comes in the first quadrant where we have positive current and positive voltage blocking capacity or capability. But practically what we see from the data sheet that the characteristic will look like this. You understand this point? So the BJT is operating in the first quadrant, and then this black what I have drawn is basically the practical characteristic what we have for the BJT. Now what this says that definitely there is some saturation voltage involved. So first let us classify the different zones where it is operating. So if I draw one more line very close to the x-axis, I can, let's say, draw over here. So what it would say that 3 different zones can be demarcated. And then this one. So what is said that here the current flowing through the device is very, very small and the voltage is going very high. So which is something like what? It is going in the off state, where we are blocking lot of voltage and very, very small current, maybe some microampere something is flowing. So this is basically equivalent to the off state of the device. And this zone is basically called the cutoff zone. We have another zone over here where we have very small voltage across the device, but the current can be very high value. So this is corresponding to the on state of the device. And this is also known as saturation zone. Now this third zone, what we see over here, where the current and voltage both are finite, basically this is the active zone, or you can say linear zone for the device. So these different characteristics we are finding due to different values of base current, say IB1, IB2, IB3 and so on. Now the meaning of active zone or linear zone is that your base current and your collector current are related through the gain of the transistor, beta or HFE, whatever you want to call. Whereas this relationship does not hold in the cutoff zone or the saturation zone. So when we have this kind of relationship between the base current and the collector current, then we say that this is operating in the linear zone, and then this is actually not suitable for switch operation. Why? Because we have lot of power loss happening in the device. V into I is very high. This is where actually the linear power supplies operate. So this zone is suitable for the linear power supplies which are operating it like a variable register, you can say. So that is why the power loss is very high, and then we need to apply lot of big heat sink, and lot of measures must be taken for the power loss. So this is not the recommended zone of operation when the BJT is used as switch. Now coming to the saturation zone. So in the saturation zone we have relationship between the base current and the collector current like this. So base current is injected more than this value IC by beta. Whereas in the cutoff zone, the base current is nearly zero. So this will ensure that your device is operating either in the saturation zone or in the cutoff zone, which is the ideal situation for it to act as switch. Clear? Now, based on this characteristic, we can actually have the equivalent circuit for the device. So we are never operating the BJT in this zone, the active zone. That we must be clear when we are using it in the power electronic converter, not in a linear power supply. Now, when we talk about the on state, so there is some voltage drop associated with that, which is called VC sat. So the characteristic is actually taking a very steep rise only after this voltage, and this value is something like 0.2 volts or so. So this is called the saturation voltage. and then it is very steep. That means the equivalent circuit is like this, where this is the direction of flow of current. And when it is off, because there is almost negligible current flowing through the device, so it is as good as open circuit. So again, we can say that the power loss here is basically VC sat into IC, and here it can be regarded as 0. Correct? Fine, clear up to this point?
Yes, sir.
So wherever we had a requirement of blocking a positive voltage and conducting a positive current, this kind of device, say BJT, can be used for that particular switch operation. And we have to ensure the operation as switch by maintaining the base current like this. This condition must be fulfilled. Correct? Now let us move to the third switch, say MOSFET. So typically it is drawn like this. And here we are talking about N-channel enhancement type MOSFETs. So there is something special about this, about all the MOSFETs actually, that they have a body diode. Now, what is the role of body diode, that we will discuss later. But as of now, let us focus on the MOSFET. So again, this also has 3 terminals, the drain, source, and gate, where gate is basically the control terminal. Now, the difference between BJT and MOSFET, if you see, the BJT terminal is basically connected to this end, and this is basically the current injected through the device is controlling this. So this is also called current controlled device. Whereas here, in case of MOSFET, we do not see any connection directly from the gate to the device. There is some gap. So these are basically voltage controlled devices. And whenever this gate source voltage is more than the threshold value, then we see that device is going into conduction or different modes of operation. So if we see the characteristic quickly, so now, from the manufacturer side, it is recommended that the MOSFET must be operated with this polarity of voltage. That means it can block this voltage easily, and also it can conduct current in the direction from drain to source. Correct? So which means again the ideal characteristic will look like something which is there in the first quadrant. So it is blocking some positive voltage and conducting some positive current. Now, the practical characteristic actually looks like this. And so on. Maybe sometimes it is drawn like this also. Now, here also we can have different zones marked based on how much VGS you are injecting, VGS1, VGS2, VGS3, and so on. So first zone could be this. This is again similar to BJT, it is active zone, and sometimes called as linear zone for obvious reasons. Now the second zone is here, where the current is very small and the voltage is pretty large, which it is basically blocking. So this you can call as again cutoff zone or off state. Now the third one is here, which is basically coming because of this linear characteristic over here. This is called saturation zone.
Sir, hello.
Yes, AJ.
Sir, I think in MOSFET it like it's reverse. The first thing will be the active region and the constant one will be
So
the
it will be ohmic
saturation.
region.
So the definition for MOSFET, when we say that what is called linear zone or active zone, many times it is confused through what is linear. Whether the characteristics, see the difference between BJT and MOSFET, if you realize the BJT characteristic is pretty steep, whereas here this is going much tapered. This is having a characteristic which is passing through origin and it is tapered. So the behavior of this device in this zone, let us say if not name it immediately, is something like a resistance, isn't it? Now that is why somewhere we see terminology which refers to this as some linear zone and refers to this as a different manner, saturation zone with more than threshold or something like that. So, but what we are operating is basically the device in these two zones where we have very less current flowing through the device and high voltage blocking, and another place where it is behaving like a resistance only. You understand the point?
Yes.
So this is called RDS on, the on state resistance what the device is offering. Correct? So all may be very, very close. What I have drawn as different characteristics, these may be very, very close. So whenever you have this relationship maintained, the device behaves like a resistance. Correct? So we operate the device in these two zones only. This is the off state and this is the on state. Now terminology may be different based on how people are referring it to. Whether they are referring to the characteristic or referring to the operation. So here we call it saturation or on state when it behaves like a resistance simply. There is no further change on the voltage and current of the device with the gate. Clear? So now, similar to BJT, we can draw the equivalent circuit. So off state is very, very clear, again, not having much current flowing through it. So it's like open circuit and power loss is also zero. Whereas on state, as I told, this is basically like a resistance and the value is not very small. Sometimes it can be as large as something like 800 milliohm or something like that for lower current rating MOSFETs. Now the power loss through this device is basically whatever this ID is flowing, ID square RDS on. So this is the conduction loss which occurs in the MOSFET whenever we operate that in this zone, right? The difference what you must notice between the BJT and MOSFET is the characteristic what is starting at a non-zero value for BJT and it is starting at origin for the MOSFET. This difference you must notice. That is why we do not have any saturation voltage in the equivalent circuit over here for MOSFET. Fine? Is that clear?
Yes, sir.
Good.
Yes, sir.
Now, one more device we may consider because this is very much popular. So insulated gate bipolar transistor. This is basically we can say a combination of BJT and MOSFET. Because if you notice what is happening in BJT, the power loss is basically linearly proportional to the current. So your power loss will rise like this with current. Say this is PL, this is your current, IC flowing. For the MOSFET it is I square R. So which means initially it will be low, but after a certain current value, it may surpass the power loss in this BJT. So which is why for low current applications, we go towards the MOSFET because the power loss is lower. But whenever we deal with high currents, we see that the BJT power is coming lesser than the MOSFET. So for high current applications or high power applications, we go for BJT. This is the advantage of BJT when we see from the power loss point of view. But the problem with BJT is that it needs current to be injected in the base for maintaining the on state. So which means there is certain amount of power loss happening on the base side always. So that disadvantage is improved in IGBT. We have the characteristic which is very, very similar to BJT and the control which is very, very similar to MOSFET. Understanding my point? So when I say characteristic is very similar, the recommended blocking voltage is in this polarity, collector to emitter, and the direction of current is from collector to emitter. This is what is recommended from the manufacturer's side. So very similar to what I have drawn for BJT, this also has the saturation voltage and then the characteristic is very steep. So resistance involved with this slope is very, very small. So almost this VC SAT defines what is the equivalent circuit when it is conducting. The other things are very, very common, very, very similar to BJT. Fine. Okay. Now we have understood different switches which can operate in different quadrants. So this also can operate in the first quadrant because positive voltage and positive current blocking, current conduction and positive voltage blocking characteristic is there. Now I have told that the MOSFET is having one special thing which is called the body diode, and this is invariably there. So when the MOSFET is manufactured, this is by default there. So what basically this diode does, that apart from this direction of current conduction, it allows the device to carry current in the reverse direction as well. Understanding my point? So here what we see is basically can be called as a composite switch. So individual switches are giving us some characteristic, some quadrant of operation. But if we combine two switches together, say MOSFET is naturally with diode. So now let us talk about only the ideal characteristic, because the actual is very, very close to the ideal, so it is fine. So here what is happening when we have this diode attached to the MOSFET, and if you notice the direction, this is called anti-parallel. What is meaning of anti-parallel is that if the current conduction for one device is in this direction, the diode is having opposite direction of conduction. Correct? Now, what freedom this is giving to us, that apart from having this quadrant of operation for VI, it is extending the operation to the other quadrant as well. So now we have two quadrant switch. Similarly, if you combine the body diode, combine any diode, let's say in anti-parallel condition with BJT or IGBT, you can realize the extended quadrant of operation. So similarly, it can be connected to any other, let's say BJT also, IGBT also, and we can realize now two quadrants which can be operated with this composite switch. The diode can be connected, let's say in other manner as well. Say I am having the BJT and I connect the diode in this manner. So what it will do if I connect it like this?
Unidirectional current and bipolar voltage blocking capability.
Yes, so current still has only one direction to flow. Correct? Diode cannot permit the reverse direction, and BJT is not recommended to be used for reverse direction of current. Then what additional thing this is giving, that if you apply this polarity of voltage, the BJT can block. And if you apply this polarity of voltage, the diode can block. So now our characteristic is extended for both the blocking voltages, positive and negative, and positive direction of current. So first and second quadrant both are covered. Understanding my point? So if we need a switch which needs to block voltage in both sides and have current only in the positive side, then we can simply have this type of connection, which you may call as anti-series connection. Fine. So now how to make switches with all four quadrant operation? So we can have, let's say, one example if I give, and you can think of more alternatives. So if you connect two MOSFETs in this manner, and this is the terminal where we are talking about the blocking and conduction. So what we see that this combination can permit current flow in either directions, here as well, here as well, here as well. Both the directions of current flow is permitted through this combination. And then the voltage blocking can be there like this, or it can be there like. So with respect to this, we have to see. So it can block like this. Okay. So when we are connecting the parallel connected devices in series, we are realizing the four quadrant operation. Similarly, when you connect series connected devices in parallel, you can realize again this can give four quadrant blocking and both quadrant conduction. Understanding my point? So this is how we can realize anything by combination of different switches. Now this is what we are going to use for our power converter realization. This part is little bit important because anything further what we will discuss will be based on all these things. So now let us talk about the realization of buck converter. So what do we have in buck converter? We have a voltage source, then SPDT switch connected in this manner. We have the inductor, capacitor, and the resistance. Fine, right? No confusion in this. So different states what we can draw for this circuit is, let us say when the switch is connected to PT1, so I will draw it, let's say like this, and PT2 is open. Now, if I ask you like in which direction the current is flowing through the PT1 switch, in this direction, right? And how about the blocking voltage of PT2? So obviously
Supply.
P is connected to this VG and T2 is connected to ground, so polarity is like this. This is, we say, on state, right? Now, when we talk about off state, what do we have? Okay, now what is the direction of current? For PT2?
T2 to P. T2 to P.
Yes. Because inductor current, once it is set in this direction, it cannot be changed suddenly. So it will continue flowing in this direction. And what is the blocking polarity for PT1? So T1 is at higher potential and P is connected to T2, T2 is connected to ground. So polarity is this. Correct? This is fine, right?
Yes, sir.
Any confusion in this one? Now, if you individually see the switches PT1 and PT2, you will be able to understand which device can be suitable for this operation. So for PT1, let us say what we have current conduction in this direction, which is also the polarity of the voltage. So something like you can say first quadrant operation is done over here. So for example, you consider that direction of current decides the, wherever it is flowing, that is the positive direction. So current is always considered as positive here. So then voltage is along that. So this is first quadrant. It is conducting the positive current and blocking the positive voltage. For PT2, it is reverse. The current is flowing from negative to positive. So PT2 is going something like second quadrant operation, where the current is positive but voltage is negative. Is this clear or not?
Yes, sir.
You are able to see the polarities, right? Plus, minus, and then how it is changing here with the direction of current. Correct? Now you tell me, what is the choice for this PT1 and PT2? What should be there in place of PT1?
Sir, at PT1, BJT or MOSFET can be there, sir.
Yes, any active
And for-
switch can be there, whatever we have discussed so far. So we
And
can have
for-
IGBT, or we can have BJT, or we can have MOSFET.
Or MOSFET. Yes, sir.
Fine, no problem in that.
No, sir.
How about this PT2?
So diode should be there.
Their only option is diode, nothing else. If we are targeting for this kind of power operation or the power conversion operation, isn't it? So that is how we realize the famous buck converter circuit, which is something like this. Because it is MOSFET, so I have drawn the body diode. Otherwise, this is actually not necessary here. Correct? So, hence, we get this combination of switch for the buck converter. The conditions for boost converter will be different. So, quickly we can see what all switches we get over there. So what we have the voltage source, the inductor, then the SPDT switch, we have capacitor, and we have the resistance. So two possibilities quickly we can draw, and we can mark the polarities. Let's say P is first connected to T1. Okay, now which direction the current is flowing?
P to T1.
P to T1.
And what is the polarity of voltage blocking over here? T2?
P positive and T2. No, sir. P negative.
Positive.
P is connected to T1, T1 is connected to ground, so this is ground.
P negative, yes, sir.
So the polarity is like this. Okay, now the second configuration we go quickly. Okay, so now what do we have? What is the direction of conduction?
P to T2.
P to T2.
Okay. What is the polarity of blocking?
P positive, T1 negative.
Obviously. So T1 is at ground or negative terminal of the battery. Correct?
Yes.
Now you see here about PT1 how the current and voltages are placed. The current is again flowing from positive to negative for PT1. For PT2 again it is from negative to positive. So which means PT1 is something which is operating in the first quadrant. And PT2 is something which is operating in the second quadrant. So what are the obvious choices for this? So we may have BJT here and we may have diode here. So that is how we realize the famous boost converter as any problem in this? Yes. Fine.
Yes, sir.
Okay. Now, before moving further to modeling and other things, one more point we can add in this. Let us say when we are defining our buck converter, boost converter, this is all only unidirectional power flow. Now, what if we want power converter with bidirectional power flow? So what will happen when you have, okay, let me draw the generic switch alone. So bidirectional power flow means what? Sometimes the power is fed from this side to this side, right? That means the current can go negative. So if this current is changing its polarity, obviously this will also change its polarity. Understand the point? Let's say when we are saying that we are maintaining volt-second balance, okay, we are having unidirectional power converter, which means something what is known as continuous conduction mode, the current is positive going between these modes. Now we reduce the load. What happens? This comes closer and closer to the zero axis. So before entering into DCM, there is something called boundary where it is touching zero and then it is going up. If you reduce the load further, what may happen? The current will rise and then it will fall and it will remain zero for some time. This is called DCM mode, right? Discontinuous conduction mode. Now, instead of this going and staying at zero, can there be possibility that it goes negative?
Yes, sir.
It is going zero. Why? Because we have put a diode which can conduct only in one direction. It cannot permit current in this direction. You understand my point? Now let us say we want to take current in the other direction. So what we need basically from this PT2, that this should have bidirectional current carrying capability. Isn't it? So then slowly when you have that capability for PT2 and PT1 as well, you may start having a current like this. Understand the point? Now average current is basically negative, which means what? Power is flowing from this side to this side. So how can that be made possible? It can be made possible only if both the switches have this capability of bidirectional current carrying. If they both can carry the current in both directions, positive as well as negative, you can have this capability of bidirectional power flow. So what you need basically, already you have diode. You need a switch which can conduct in the other direction as well. And definitely it must be a controlled switch. So something like MOSFET with body diode, if you connect at that point, this can serve the purpose very well. Isn't it? So MOSFET will provide, but definitely the gate signal must be given appropriately. So this can provide you alternate path for the current. So then the current going negative could be possible. Similarly here we are putting the MOSFET with body diode, which means already we are having this capability for the negative current flow. So if we draw the converter with these capabilities, this can be used for bidirectional power flow. This is also called synchronous buck converter, where these two switches are operated in alternate manner. If you are giving signal S to this, then S bar signal will be given to this, so that you allow it to be turned on so that it can conduct the flow. It can conduct the current. Fine. This is clear to all of you, right?
Yes, sir.
Now the question comes, how do we operate this converter? Let's say if someone asks, okay, you have designed the converter, but for controlling it, you definitely need to model this mathematically. For controlling this converter, we do need to model. Now, what is meaning of model? What is meaning of model?
So state space analysis.
Okay, that is one step ahead. But what do you understand by model? Simply
Sir,
model
actually
means,
the mathematical.
yes, we are looking for some expression or some
Yes.
function which can define this, let's say buck converter or any power converter in general, which can define. So if I draw a block, there must be some input, say X, and some output U, and this U should be basically function of X. You understand the point? Getting my point?
Yes, sir.
Yes, sir.
Okay, are you getting the point?
Yes, sir.
Yes, sir.
So this is what we are looking for. We are looking for a function which can define what a power converter is. Now, when we see it from this power circuit point of view, you have input voltage as Vg, output voltage as V0. There is no clarity on what we are feeding or how we are controlling these devices. That was the question. How do you generate the T on and T off pulses? How do you generate? There must be something. No, you cannot keep changing this Vg voltage to realize any VO voltage. Or you cannot just manually give some pulse on and off to this. This must be related with some other parameter, some control parameter. Understanding my point? Let us say if I tell you that I want to generate certain amount of VO and I have certain amount of Vg. So what you will tell me that, okay, you operate it with a duty ratio, something like D. Now I will ask, how do I generate this duty ratio? So simple solution, what is said is basically, let's say to maintain the T on and T off and let's say switching time properly, you compare a reference voltage which is equivalent to the output voltage with respect to this ramp carrier. And this ramp carrier is basically having time period which is equivalent to the switching frequency. And you define that, okay, whenever this is my reference, some signal I have generated, and the maximum value for this carrier is, let's say, 1. So it is changing from 0 to 1. So I tell that, okay, whenever my Vref is greater than Vramp, what I do, I turn on the circuit. That means I go in the on state. So if there is some gating signal, I give that as 1. So this becomes 1 and this goes to 0. That is how the gating signal is given to the device. Now, obviously, when the device is operating like this, we know that the pole voltage is generated in the similar manner. And the output voltage is nothing but the average of this pole voltage. These levels are VG and 0. Any doubt in that? So I should write it like average value of VP, which is basically D times of VG. Now, what I'm trying to do, I'm trying to correlate my output voltage with my reference voltage. Ultimately, this is what as control variable I am giving. If I change value of Vref, definitely this width will change and then my output voltage will go higher. You understand this point, right? So if you match with this, let us say this is my T on duration, this is T off duration. If you match and use this similar triangle principle, say this is V peak. So definitely Vref by V peak is related to the time period like this. Or we can say that V reference is basically equal to T on by Ts is D. So generally we keep Vp equal to 1. So directly this Vref is related to the duty ratio D. And we can say that our output voltage is nothing but Vref times of Vg or the input voltage. So we have a relationship between the output voltage and the control input. So this is the function which defines what input you provide and what output you are going to get for the given DC bus voltage. You understanding my point? So this is the function which I was talking about, Vref, and this function is only a constant gain, which is equal to the DC bus voltage. So the block what I have drawn over here for the power converter modeling, I can simply write again, say G, and I can give Vref, and what I will get as output is VO. So I am able to model this mathematically. You understand this point? So what is the value of G over here? Is that clear or not?
Yes, sir.
When we are going for control, this modeling is necessary. We need to know what we are dealing with. Correct? Shambhunath, everything all right?
Yes, sir.
You are muted.
Yes, sir. Yes, sir.
Yes, sir. No, so your hands are on your head, so that's why I am worried. Is everything all right
No,
or
sir.
not? Or
So
everything
actually,
going?
this is the actually, sir. When the load voltage will be changing, then this will be working like a closed loop fashion, sir.
Yeah, I will come to the closed loop, but as of now, we are defining how you can control the output voltage through a control signal. So this Vref can act like a control signal. Let's say a box is there, which is basically our power converter. Say this box is there. And we give a control knob is there. No, so we change that knob reference value and it gives the output VO.
Okay, sir. Okay. Yes, sir.
Understanding my point?
Okay, sir. Yes, sir.
Okay, and this is what we are saying is nothing but a constant G, or you can say the DC bus voltage VDC is just multiplied to the Vref.
Okay, sir.
And whatever we are getting is related to this reference like this.
Yes, sir.
You understand my point?
Understood. Yes, sir. Yes.
So this is how we are basically modeling our power converter. In general, any power converter that we deal with, that can be modeled as a simple game, which is basically nothing but VDC or VDC by 2 or something like that. So this value may change according to what topology you are having, what configuration you are having, but more or less this is related to the DC bus voltage, which is constant, or the input voltage what we are giving for the DC-DC converter. And the reference voltage changed in a manner that it controls the output voltage. You understand my point?
Yes, sir.
Okay. So when we have clarified this part, okay, still any confusion in this, you please ask, because next things we are going into modeling of the control system. Okay. Any confusion in this part? Ajay?
No, sir.
Is it fine? Ashish, Sampan, another Ashish?
Yes, sir. It is fine.
Yes, sir.
Good.
Yes, sir. Yes, sir.
Uday Kumar?
Yes, sir.
Good, good, good. Okay, so now we have done the realization of power converter. So which means if we have a motor, let's say a DC motor is there, DC separately excited motor. Correct. If I ask you that you have to simply operate this motor from 0 speed to full speed. So what you can do? Kumar?
Yes, sir. It is
Some noise is coming from your side, Sukumar. So we have this DC separately excited motor. Let's say we want to simply run it. We are not worried about at what speed it is reaching, or whether it is controlled properly or not, whether the dynamic performance is good or not. What we need to do, we will connect this DC motor, which we want to operate, to a power converter, which will basically give the output voltage corresponding to our reference. So we know that here the omega is proportional to or kind of related to the input voltage, no, whatever we are feeding to the motor. This understanding we have, right?
Yes, sir.
Correct. So now if we have to simply operate this motor, it is okay. We can operate, there is no problem. We can provide some reference voltage to our controller, and based on that, it will give some gating voltage, which will be generating some output voltage here, and it will operate the motor. But now if I tell you that we have to operate it in a manner that its dynamic response should be very good. What is the meaning of dynamic response? This rise in speed, or when it is tracking the speed, this should be very, very fine. It should quickly rise to the final speed, and it should not be disturbed with any load coming on the motor or any other disturbances coming on the motor. The speed should not be disturbed. You understand the point? So this is what we are trying to do now. So for that, what we need, definitely we need some kind of control implementation. This control board which I am talking is physical. Say DSP or something, some control board is there. But inside you need to implement something like a PI controller or P controller or PID. Okay, how do you design that? The first question is that. So definitely for doing that, we need to model all these components. So one part we have done, we have modeled the power converter. There is no problem in that. Correct? The second part is basically we have to model the DC separately excited motor. So we all know that this is the equivalent circuit for separately excited motor where the flux is kept constant. Fine, right? No doubt in that. So I'm applying some field voltage, some RF, LF, these parameters are there. On the armature circuit, I have RA, LA, and then it is generating some back EMF voltage when running at speed omega. So I'm applying armature voltage of VA. Now, how these quantities are related to each other, that is what basically we say is the model of the motor. So first we can do the electrical model, basically writing the KVL equation for this armature circuit. So what it will be? We all know it very well. So nothing to explain. This is fine, right? Now EB, we know that it is related to what? Some constant times flux times omega. Fine, right? EB is for separately excited motor, EB is defined like this. Now because flux is kept constant, so these two can be combined together and it can be, let's say, taken as C. So equation what we will have basically, so this is the electrical sub-model, or we can say the electrical side model of the separately excited DC motor. Now mechanical equation also we can write similar to what we have done earlier. Now here the tau E, the electromagnetic torque, is again connected to the armature current in this fashion. K times the flux times of the armature current. And because flux is maintained constant, so again this can be taken as C. So the equation can be written as fine, right? So we have modeled both the things. Now, if you take the Laplace transform and try to write in terms of block diagram, what you will have as system basically, you have input VA, which is basically from which the back EMF EB is deducted. Then you have the RL circuit, which is generating basically the armature current. And then this armature current, when multiplied with this constant C, is generating your electromagnetic torque. From here, your load torque is subtracted. And then what you have is basically first order speed, this. So B plus Sj. And then this is coming out as omega. And omega is basically responsible for generation of EB. So this is the block diagram for separately excited DC motor. Now this plus the converter. Now where is the power converter? Power converter is used for feeding this voltage. So where it can come? It can come simply before the VA. So this is, say, VG, the gain. And what is the input for this converter? The reference voltage, what you are feeding. So this block diagram is for the DC-DC power converter plus separately excited DC motor, where you have the reference fed here and the output is generated here. Am I clear? Okay. Now few questions before you come for the next class. Why do we need closed loop control? Or why do we need to control it? What's the problem with if we go with no control in this system? Anyway, we are giving some reference voltage, it is generating some omega. What is the problem, or what are the possible problems that may occur in this? So this question you have to little bit think. So, and possibly revise some of the body plot and these kind of concepts which you might have read during your control classes. So which is what we will use to establish how the controller is designed for this kind of system. The closed loop control. When we have to design the PI controller, I mean, how would you design the KP and KI parameters of the system? What rule is followed? What expression you can get so that it can be universally applied to any motor. Understand the point? So with these questions, I stop the class over here, and tomorrow we deal with more things related to the control aspect. Tomorrow and day after tomorrow, 2 days, it will go completely into control domain, and which will be completing your DC separately excited motor closed loop control. And then we will move towards the induction motor. So any questions up to this point? Sampan?